So last week you took a practical and a midterm. The practical, I believe, have all been uploaded to the Google, as a Google Doc to the 471 account, or at least the TAs indicated that they appear to all be uploaded there, so that's good. I have most of the written tests. I'm still waiting for 2 schools to send me PDFs of what their students did. Hopefully those will show up today. If not today, tomorrow at the latest, and we can I can begin grading the written part, and the TAs can begin grading the practical part. We are switching to a new topic. The topic today that we're going to be discussing this week and a little bit next week is finite element. The finite element is based on chapter 17 in the textbook, and so you should begin reading that material. That material is at best an overview of how finite element modeling is done. For students here at BYU, what you would want to do, if you wanted an in-depth background on finite elements, you would want to consider taking the ME 501 and ME 506 courses. They both are excellent classes. The 501 is more of a practical approach where you do a semester of finite element using a commercial tool. In the past, it's been ANSYS. I think they're now looking at doing Abacus or Nastran. But it's just a standalone 16-week exposure to kind of commercial finite element. The 506 class is where they begin kind of talking about the mathematics of finite elements, and they go in and derive at least 4 finite element methods. We mention them in the lecture today. We don't take any time to go through the mathematical derivation, but we talk briefly about them. So this is but a brief exposure to a very important area in engineering, especially in the considering that the problems that we are dealing with today are much more complex and much more difficult than they were a few years ago. If you think back to your classes on strength of materials or the theory of elasticity, those methods that were taught here at BYU or at other universities with similar titles, those subjects focused on pretty simple materials. They focused on pretty simple shapes. They focused on a fairly straightforward general approach to figuring out stresses or deflections in those shapes. I don't know about any of you, but when I took those classes, I would get to the end of a chapter, and in my mind I would say, I wonder how many times this cantilever beam problem has been solved. If it's been solved once or 100 or 100,000 times or 1,000,000 times, do I really need to solve this over again to gain an appreciation of what a cantilever beam does? Well, they eventually moved to more different loaded, superimposed loads. They moved to different kinds of constrained models. But again, they're all pretty simplistic. And the first internship that I went on at Boeing, not once did they give me a cantilever beam problem to solve. Or did they give me a simply supported beam and say, solve this problem? What they gave me were problems that the simple approach wouldn't work on, or I didn't have the understanding of how to simplify it into one of those basic shapes. So when we think about the modern engineering has moved far beyond kind of what's found in those fundamental classes. And we need numerical tools to actually assist us in solving these complex shapes, complex loads, very difficult boundary conditions, and things like that. Most of you, I'm sure, have opened the hood of your car or opened the hood of your parents' car, and you've looked underneath the hood, and generally what you see is kind of a spider web shape of material. It's a sheet metal shape that's been bent, twisted, formed, and cut out into a shape that is the lightest weight and yet provides the best structural support for some 150, 200-pound gorilla sitting on the hood of your car. I mean, the whole idea is to provide support underneath that elegant surface and provide it in a way that is still very light, but yet very strong. There is not a problem in a standard finite element book or a materials, strength and materials book that says, here's a spider web for the underneath surface of your hood, go and solve that and figure it out. So we need different tools. It was back in the 50s when finite element was being developed. And so about the time that computers started being developed as these massive rooms with lots of tubes. There weren't any ICs or anything like that, but finite element kind of came into play and was viewed as being possible because of the computer that came into existence. And so the approaches that were developed dating back to the 50s are really in these three forms. They were either a finite difference approach, a finite element approach, or they were a boundary element method that was developed to solve these complex problems. The book talks generally about each of these three. If you want to get a better understanding, then you're going to want to take an advanced graduate level kind of finite element class. The solution of field problems is based on kind of the discretization of the complex shape into smaller solvable problems. And so that comment is basically to say we take a model, an object, and the first thing that we do is break it down into very simple elemental shapes that we know how to evaluate and work with. The types of problems, these field problems that we can work on using finite element methods, are everything from stress, fluid mechanics, heat transfer, diffusion, vibration, any kind of electrical or magnetic field, and the list kind of goes on and on. So finite elements is very widely, broadly applied to field type problems. So in the textbook, the author kind of lays out a procedure for doing finite element. The first step that he talks about discretization. And so in the book, if you're wondering where should you be spending your time most in reading, it's really in the topics, it's in the sections that are covered by this outline. So there's this section that deals with discretization, where it's basically breaking it up into elements and nodes. There's a section that deals with kind of the approximate solution for a single element. So there's this generalization to a element. The element is either linear, quadratic, or cubic, or it goes even higher than that, but generally it's one of those three. He then talks about taking that element, that single element, and applying it to all of the elements. And when you apply it to all of the elements of the model, what in effect you are doing is filling an element matrix. And these element matrices can be gigantic. Pratt & Whitney talks about doing CFD models that have 10 million elements in their model. And so if you've got a 10 million element model, you've got a very large matrix, probably on the order of 10 million by 10 million to actually work the thing. When you're developing it into this element matrix, you're really setting up kind of a stress matrix, a mass matrix, and a load or force matrix. The next thing that you have to do is you have to kind of generate the global system matrix of equation. And that's just basically summing up the equilibriums. You then solve for the unknown nodes. And you interpret the results. So that's the basic outline of chapter 17. There's more stuff. But the author goes through these kind of 6 basic steps. And that's where you ought to kind of focus your reading. Now we're going to take a minute and kind of talk about each one of those. So in the discretization of the model, the first question that always comes up in the literature, the author of this book talks about it a little bit. It's really the question of, do I put nodes down and then create elements? Or do I create elements, and in the creation of the elements, I identify the nodes? Well, the nodes are the corners of any element. So we'll see that in just a second as we define what nodes and elements are. But it's always this question of, well, should I first blast out a bunch of points called nodes, or should I blast out a bunch of elements and then populate the elements with nodes? And it really doesn't matter. You need both. And the reason that you need both is because the node is where all of the results are calculated. So the solution to the matrix problem is finding values at every node point, and then it can interpolate a value for any point inside the element. Okay. So nodes come in kind of 3 versions. You have a 1D node, a 2D node, or a 3D node. The nodes locate at which the solution is obtained. The nodes must be shared across element boundaries. So if we have this blue element and we have this red element, and they are intended to be next to each other, then the red and blue elements must be the same element, or they must be tied together with a rigid. So if this were an assembly, if it were a part file, they need to be exactly the same. If it were an assembly, and the blue represented one part and the red represented an adjoining part, you would need some kind of a connection between the blue and red to transfer the load across the assembly. And so generally you would tie these together with a rigid. Okay. Nodes are where the loads are applied. That's changing. There's some research out where they're beginning to say, well, if I put a load on one of the edges of the element, what I'm really trying to tell it to do is distribute that force